All right, guys, good morning. Yeah. Welcome to Brno, some from very local and some very far away. So all time zones, the first few days will get adjusted. My name is Sanjeev Khudanpur. I am at Johns Hopkins University, and along with Honza and my colleague Paula Garcia, we are the organizers of this workshop. Honza will start you off with a little bit of an introduction and everything. I just wanted to get my hello in before him so that I can get out of the way. But just to tell you a little bit, these workshops have been going on for a long time. And as they keep going on, one of my colleagues in academia remarked, we academics, we've been around, and our students keep getting younger every year. Well, no, that doesn't happen. They come in at the same age. We keep getting older. So this workshop is actually older than many of you in this room. It started in 1993 and 94. Actually, not even at Johns Hopkins. It started at Rutgers University. And my esteemed colleague, Hinek Hermansky, who's sitting over there, was actually at the Rutgers workshops. And if you catch him during the coffee break, he will tell you how much fun it was and what we were doing in those days. But in 95, they came to Johns Hopkins, and they've been there since then. And I will tell you more about them at another time. What I wanted to say is a little bit about the summer school. So around 98 is the first time we had undergraduates in the workshops. Until then, it was only senior researchers and maybe a few PhD students here or there. And once we started getting undergrads, we realized, hey, we need to have some more teaching-related things, not just research, because these are young people to the field and so on. And the first couple of years, it was all homegrown. I'd just round up my colleagues in Johns Hopkins and say, hey, guys, let's put together some lectures. And then it grew a little bit, and the North American Association for Computational Linguistics got interested and said, hey, we want to support this, and we want to have more lectures on NLP. And we said, okay, and they started sending students to it. And slowly it has grown out to be a little thing on its own. For 2 weeks, we organize lectures, labs. It always still has a local flavor. So when we did it in France 2 years ago, there were a lot of French lecturers. Here you'll see the best that the Czech universities have to offer, Brno in particular. But the focus always is to take a theme or a set of themes for each day and give you all an introduction to it. And hopefully you'll take it in that spirit. I know some of you are graduate students who are very experienced, and you might find some of the days boring because it's your specialty. Switch your roles, and in those days act like teachers. And then other days, sit and listen when other experts tell you what's going on. So let me just stop there and hand it off to Honza. Honza, please get us started.
Okay, thank you very much, Sanjeev. I'm Honza, and it's my pleasure to see so much of talent, like international one from all possible countries and continents here at FIT. So FIT is the Faculty of Information Technology, and BUT is the Brno University of Technology. You might have some problems pronouncing Brno, so we can give you some training during the breaks. So as Sanjeev said, this workshop is running for a long time, and it bears the name of Frederick Jelinek. That was actually Bedřich Jelínek, a Czech-born computer scientist that was basically the father of the statistical speech recognition and statistical natural language processing. So it bears his name. Okay, I have just a few practical slides on how to survive practically. First, I am quite happy that everyone made it to Brno, despite yesterday's weather, as some of us experienced yesterday in the afternoon. Then just something about the people who is behind. So Sanjeev and Paula from Johns Hopkins University are the long-term maintainers and keepers of this workshop, and I have the pleasure to be the local scientific, not only scientific coordinator. We have two very important people that you have already seen in the morning. So Renata over there, and Radim over there, and these guys actually were the ones responsible for getting you here, getting you the visa, getting the rooms, getting everyone doing what he or she should do. So big thanks to them. I just couldn't make it without them. We have also some student helpers. So I think you met already Martin, Jaroslav, or Jarek, and Katja. They will be just here all the time, ready to help you with anything. And Katja will be the special one. Where is Katja? Yeah. So Katja is there, and there is Martin, and there is Jarek just next to him. And Katja is the special one helping with the audio-visual issues. So in case there is any trouble with the projection or streaming, just ask her. Then how the thing is organized. So I think you experienced it already in the morning. At 8, we have the bus departure from the dorms. 8:15, the breakfast, which was, I think, pretty good this morning. From 9 to 12, we have the morning program that is taking place here. So this lecture room is E112. We will be just kicked out for 2.5 days from Wednesday afternoon because there is another event running at the faculty. So we will be moving to G202, which is not far from here, and it will be marked. Then at 12 we have lunch in Mensa in the same place as we had the breakfast. Please do not forget the tickets. No ticket, no food. And from 1 till 5, or let's see when we are ending up in the afternoon, we have the afternoon program again here in E112, or Thursday, Friday, it will be another lecture hall. And just special for today at 5:30, we have the welcome picnic, well, right in front of this lecture room over there. And there will be some food. It's a non-alcoholic one because we are pretty sure you can get some alcohol later in the evening in the downtown. So for the detailed program, we will have a special web page that I think you have seen. I won't go through the program for all the days. I think we managed to get like quite excellent speakers, and I think we will be just introducing the speakers as they are coming. We just try to get the best from FIT, from Czechia, and from some neighboring countries such as UK or Poland, where we have some influence. Okay. So that was the program. Then a little bit of practical info. Radim and Renata did a great job on this JSALT 2025 welcome guide. Now it has something like 20 pages, and it's really like comprehensive document. So please take a picture of the QR code if you haven't already seen it. There is everything. Then for another practical thing, you might need to connect, I guess. So the people that have accounts with any educational institution worldwide should be able to use EduRoam. And those who have some problems with it can go to the VUT. It's not BUT, it's VUT, because in Czech it's VUT, it's Vysoké učení technické. It's like very complicated name. And the account is JSALT minus summer VUTCZ. And who did this password? Summer on the beach. Okay. Only on the weekends. Otherwise, it will be work. So that was the practical things. There are actually not too many dangers here. Czechia is quite a safe country, so we don't have violent gangs or wolves or like mountain lions and stuff like this. But we have a very dangerous animal. It has 3 millimeters, and it's called a tick. So please be very careful if you are sitting or laying somewhere in the grass. We have very nice season with plenty of grass. It's cool just to sit or to lay in it. But then these guys can get on you and can bite into you. So if you discover a tick on your body, just try to remove it immediately and then observe the place for what's the recommended period, a week at least, or maybe 2 weeks. In case you see some nasty stuff like some red circles forming around, please tell us immediately because the tick might be infected and then we need to get you to doctors to administer some antibiotics. Actually, they can be infected with some very nasty diseases that you don't want to get. And the last is more funny, so hangover, I think everyone can like handle beer, but we have words ending on ice, like slivovice, meruňkovice, hruškovice, and so on. They are spirits, and very often they are strong spirits. And I think like Czech people have usually some experience with these, but you might be less experienced. They tend to be strong, and they tend to be treacherous, so be careful. And just a couple of to-dos. So please, people that are sponsored by JSALT, make sure that you have an account in Czech crowns. We ask you it by mailing, so Revolut, Wise, or something with the local bank, because the financial transfers will be done in CZK. Then stop with Renata to get the access cards. I think most of you already have them, to get the JSALT folders. And there will be quite some paperwork to sign, some contracts and some declarations and so on. Then, well, of course, enjoy the summer school. So please listen, react, and question our speakers. They will be happy to have like some attentive folks in front of them. And also, if there is some examples of code, some demos, we'll be very happy if you run them, try them, comment, ask, and so on. And then, of course, outside of workshop, enjoy Brno and Czechia. So there is the beer, but there is also quite some nature around Brno. It's just enough to go to the terminal station of almost any bus or tram, and you can have a nice walk. There is lots of music and culture, and there are some other Central European places, like within very short distance, like Prague, Budapest, Bratislava, Vienna, even Krakow is easily reachable. And that's it, guys. We should thank to our sponsors. So now we have them all. It's JHU, BUT, then Esperanto as the European project, Phonexia. We have quite some money from local OPJAC project funded by the Czech Ministry of Education and co-funded by European Union. And we have also sponsorship from the region, from the city, and our media partner is Brno AI, some local organization supporting AI stuff. Okay, that's it. So I think we will head start with this first speaker. So I would like to introduce, questions. No questions. Maybe like just for structuring the morning and the afternoon, we might do like always one break, and it will be up to the speaker to do a break whenever he or she wants. And if like you are too tired or too much in need of going to the restroom, just say, sir, you should do a break or something like that. Just don't hesitate to ask. So Petr is a senior researcher in our group, and he actually works and has worked in many areas from speech recognition through speaker ID. He was also one of the co-founders of Phonexia, and for quite some time he was serving as the director and then CTO of Phonexia. So he's experienced not only with research, but also with the ways on how to get the research into production. And these days, he's mostly interested in conversational speech technologies, speech dialogues, and so on. And I decided to do at least one personal remark for each speaker. So Petr is an avid ice hockey player. And this is not Petr. I took some random picture from the net because I could not find Petr's picture in like ice hockey gear. But if you see him playing ice hockey, it's actually something very nice. So I transfer it to Petr, and I hope you enjoy the workshop. try it out. How's the volume?
So, can you hear me? Is it okay, or shall we adjust it?
Maybe you have it a little bit to the side, but I'm not sure if you managed to. But I think it should be okay.
Okay. So, thanks, Honza, for introduction. What Honza didn't mention is that I was part of the teams on several workshops. One was with Hinek Heřmanský, one was with Dan Povey when we started the Kaldi toolkit, and I think 2 years back I led one workshop, one team on conversational AI. And I learned a lot on these workshops, and it helped me in my career. So now I would like to share some of the information and give you some overview what was done in past, and basically also some motivation. My talk is about automatic speech recognition, but it's not only about automatic speech recognition, because I was asked by Lukáš, can you talk a little bit more about transformers? So it goes to the newest techniques, and as you know, the transformers is not only about speech recognition, but it is about any media processing. So I will start with the classical structure of recognizer, or speech recognizer that was here for many years. Earlier, the recognizer was really composed from many blocks, and the blocks were developed separately. Now everything goes to one monolithic system, one neural networks, and it's trained basically end-to-end with the final objective. So how the classical speech recognizer looks like? There is input, speech input. Very often there was a separate voice activity detection based on machine learning, or earlier based on signal processing. Then we extracted some speech features. There was acoustic model, decoder that was looking for the best transcription, and usually there was some post-processing. We wanted not only one best result, but lattices, n best, or something more. And the decoder was using language model, or in a complex form, recognition network. With speech processing, we started with feature extraction. I won't go deep in this because Hinek will be speaking about this part. But what I wanted to say, we are working with sequences. So we take waveform that is recorded from a mic, split this waveform to small chunks, usually about 25 milliseconds long. There is some overlap, and then we do post-processing of each chunk. The most common is fast Fourier transform. We are evaluating the similarity with some harmonic signals, and the output is spectra. If we concatenate the spectra in time, we get something called spectrogram. So you can see that this spectrogram can be visualized as image so this question whether we are processing speech or whether we are processing images. Now, really, the fields are getting closer and closer. And the last remark from feature extraction, usually the spectra, the human ear is sensitive differently for different frequencies. It's less sensitive for higher frequencies, so we are doing some compression and or filtering, and we design filters that are more sensitive for low frequencies. But I won't go deeper because I'm sure Hinek will speak about it. Then about acoustic models. Acoustic models, the goal of acoustic models is to evaluate that, for example, some sound, some small acoustic unit, phoneme, or even shorter units, match what is our model. Basically, we need to evaluate that in the signal in that one frame is, for example, sound A, B, C, or phoneme A, B, C, and we are using such models. For many years, the common models were Gaussian mixture models. This is how basically how the features can look like, because the features usually it's vector with multiple dimensions, but if we plot just 2 dimensions and try to visualize the features, we will get dots, and where there is the sound, we will see higher values in probability distribution. And initially, it was quite easy to see where the features, where the data really are, because we had such models. And this was different for each phoneme. But later, we found that we can get more from a neural network. And so I will start initially with these Gaussian mixture models, and then I will show the transition from this to neural networks. Maybe a remark, initially when I was preparing this talk, many people came and asked, please include some kind of techniques. But then Lukáš and other people came, please talk more about transformers. So this is very far away. So I decided to focus more on the transformers later, but I wanted to tell you that even with Gaussian mixture models, it was not straightforward, and people tried to improve these models, developed many techniques, and these are techniques that tried or that were adapting the features to models or models to features. So if you are interested in this, we can talk separately or look at articles about techniques that were used in past. And maybe with neural networks, when the transition started, because it was difficult, because the state of the art at that time, there were Gaussian mixture models, and the Gaussian mixture models produced state-of-the-art results, and there were very powerful systems at that time from Cambridge, IBM, and people, there was no trust in neural networks. So I would say that the initial effort was that people just trained phoneme probabilities or classifier or model that estimated posterior phoneme probability, and with some simple transform, people start feeding this as features to Gaussian mixture models that work. It was not optimal, but then there was other move. People found that it is possible to get neural network bottleneck features, that you train neural network, for example, for phoneme recognition or state recognition, and then you add a layer that is narrow, and this. Okay. Sorry. Yeah. This is features that actually there was neural network that was trained for example, classification, the classification to phoneme classes or to phonemes, and you didn't use the final classes, but you remove, for example, one or two final layers from the neural network, and you use compressed information before these two layers. So I showed the images with Gaussian mixture models, but basically imagine that we have some data, and we need to, and these are placed somewhere in the feature space, and we need to separate this data. With Gaussian mixture models, it was easy because you had two models, and you had such two models, and basically, if there was higher value for phoneme, for example, A, you choose A. If there was higher value for phoneme, for example, B, you choose B. In case of neural network, we work with discriminative classifier, and it separates the classes with some hyperplanes. So here I tried to show what one simple neuron does. So it can separate class A and class B, and this plane is basically due to the nonlinearity. And here you'll see that the power of this is limited. Therefore, we combine the neurons, and if you combine already two neurons with one more in a higher layer, you are able to create shapes like this, like some islands or places, and select what you are interested the most. Now, I said that in speech recognition we work with, we work with some with some language models that were used by decoder, but for the representation of the language model was usually not. What is language model? Language model is basically probability of, we try to get some probability of the word that can be spoken, and then if we have several words, several possibilities, we can evaluate which one is more likely. So for example, here you can see we have word start of the sentence, and here we can have word car, bar, and end of the sequence. So we started with this. Between the two word labels, there was usually this probability. But for the recognizer, we needed more detailed information. We needed to map the words to our models, to our acoustic units. So here it can be, there are some phonemes, and we did this through finite state machine, through network like this. Such network can be composed. There were several techniques how to do it. The most frequent approach was using finite state transducers. So if you are interested in finite state automata or finite state, weighted finite state automata, weighted finite state transducers, look at this open source toolkit, and it's a very, very powerful tool for this. How it works? Basically, we can create several automata, several graphs, and start with language models that just, or start with language models that is G, and this is automata where we have, in case of bigram model, word on each node, and the transition between these two nodes, there is the word label and conditional probability that we will go to word if we were in some earlier words. Basically, that we will extend the sentence by one word. Then there was automata that converted or transcribed word to phonemes, and the toolkit can compose these two automata together. Create basically graph like this. And in the recognizer that people were designing, the graphs were a little bit more complex. The phonemes were not context-independent phonemes, but the phonemes could be, there could be influence of previous phoneme, next phoneme. So instead of, for example, 40 phonemes in English, there was inventory of many more context-dependent models. And this could be modeled by, again, some transducer C, and then even these contextual units were not enough, so people split these units in time to some states, shorter units in time, and this was done by this transducer H. So here are the examples how the graph was made more detailed. So we started with words, then we went to phonemes, then contextual phonemes, and then to some states. And what is the power of the toolkit I mentioned? If you create the graph directly, without any optimization, you will get a really huge graph. That it's hard to load to memory, and it's inefficient for processing because there are basically parallel ways that are equal. So the common technique was optimization of such graph, and two main techniques that are used or that were used were determinization, that was joining the nodes from the beginning with the same passes, and minimalization, that was joining the passes from the end, and then the graph was more compact. What is the decoder good for? The decoder, there are several processes. So I showed recognition graph. Based on the recognition graph, we can propose what could be spoken, what is the most probable, if we are in word A, what is the most probable next word. So this is done based on the recognition network. So we are building a tree of hypotheses. In each hypothesis is scored. One kind of score is taken from the language model, the probabilities of the following units, and the other part of score comes from our acoustic model. So I showed two kinds of acoustics model earlier, but when we are building such a tree, we are adding the probabilities, language model probabilities and acoustic model probabilities of all the words, phonemes, context, dependent phonemes or states that we see on the way. And our transcription, our best transcription is selected, or the best way is selected based on the probability of the final, at the end of the hypothesis. But imagine, if we run such process, there are almost infinite, there is almost infinite number of possibilities. So if we run it, it won't fit to computer memory. So there needs to be other process that is basically cutting some branches and make the tree of hypotheses compact during the processing, and there was the process that pruned the hypothesis. Then for the follow-up processing, we select either one best transcript, but there were possibilities to save the whole tree of hypotheses. It was called lattice, or there were possibilities to convert it to some n-best representation, that there were several best transcriptions. Now, how does the system was trained? It started quite easily because we had audio. This was our file that we recorded over mic. We had some transcription, either word transcription, in earlier days even phoneme transcription. This was done by human. Someone had to listen it and transcribed, and we created some concatenation of models. In earlier days with Gaussian mixture models, there were really several models in line. Later it was replaced with one neural network, and initially we split the audio to these models or these small units uniformly. Estimated initial models like Gaussian mixture models, trained the model. We got some parameters, but the model was not optimal at all. So the approach was to iterate until we got good model and good alignment. So we were improving model and alignment at the same time. With neural networks, they are not separate models, but there is one neural network, and this let's say states or these labels are characterized by neural network output. So each label had one neural network output, and again, how it started, we had good algorithm to train Gaussian mixture models. So initially we trained the whole system with Gaussian mixture models and used the alignment from this model to train neural network based models, and maybe even we edit or few iterations with realignment even with neural network model. Now there are approaches that can work without this phase, but this was the transition phase between Gaussian mixture models and neural networks for some time. Now let's try to summarize what are the advantages or disadvantages of Gaussian mixture models or Heidelberg-Markov models. Basically, Heidelberg-Markov models have some assumptions and that limits the ability of speech modeling that don't hold. So in this phase, there was still huge need for better modeling. The initial adoption of neural networks in speech processing started with simple three-layer networks. So people thought it is enough for some time, but it was not true. So there was need for better architectures that moved the field. And also a huge bottleneck in this architecture is that each model is trained separately and with different objectives. So there was for some time different objective for language model, different objective for acoustic model. There were algorithms how to create some, for example, conversion from grapheme to phonemes. And the training was complex. So I start with some initial disadvantages. So imagine if you train neural network to recognize what phoneme is in some features that I showed earlier. You have several features for one phoneme because this feature vector is generated each 10 milliseconds, and if we have some vowels, it can take 50, 70 milliseconds, so it is repeated. And if we train just the neural network to recognize these frames or these vectors, we can get probability that is close to 1 for several consecutive vectors. But we would like to somehow balance this, give lower value for vowels, for example, give more value or better score for positive and so on. So as I said, initially there were several objectives. Very often there was a maximum likelihood for the alignment or for the hidden Markov model part. And we started with simple cross entropy for the neural network. This is what Hinek remembers. But then, and if we look on this bias formula, basically this is likelihood that came from our model, Gaussian mixture model, or from a neural network. In case of neural network, it could be somehow transformed. This is probability of the word sequence, and this is evidence of data, basically probability of all data. And for recognition, very often this was omitted. We said it is not important. But if we look here, it's basically probability of all the other possible hypotheses. But it is important, and from maximum likelihood approaches, we move to maximum mutual information objective criteria, and there the main difference is that it takes in account even this evidence of data. And with this approach, we can train a really model that it doesn't assign the sharp probability for some labels, but it looks more like this. Initially, how to get the probability of all other sequences, we took the decoder and basically took all the other hypotheses from the decoder. But it was not practical, it was hard to implement. So then, for example, Dan Povey came with an approach called lattice-free MMI, and this was simplification. It used some phonetic language models. He connected it with other tricks like reduction of the frame rate and other objective criteria, but it was a move that increased the accuracy of the systems quite significantly. Now, one picture that phoneticians likes, Hinek likes this picture. If you have a system with small number of acoustic units, like phonemes. It can be visualized, and you can see that here is, for example, silence, here is silence, and then there are these acoustic units active. For some clear recordings and shorter recordings, it was even possible to read from such images what is inside speech, just based on the acoustic model. I think basically this maximum mutual information approach, it was powerful, and we were getting good results, but it is still quite difficult to train because of the alignment that is necessary. Then Alex Grave came with other objective function for training, and this is called CTC, Connected Temporal Classification. And the difference is that instead of producing high probability for the whole duration of the segment assigned, for example, to one phoneme, the model produces high probabilities only once during the segment, very often close to the end of the segment. And on the other parts, there was one more output from the new network called blank symbol, and it's said there is no label at this time, and the sum across all the new network outputs had to be 1. So this is other approach how to work basically with frames. With CTC, actually, you were able to get different sequences because there was the blank symbol marked as this dash here. So some post-processing was needed, and we were forced to get basically the best sequence. In comparison with lattice-free MMI, the CTC works similarly. In CTC, there is normalization per frame. In lattice-free MMI, there is normalization per the whole segment. Okay. This presentation is about transition from Gaussian mixture models to neural networks. So now I will focus on neural networks and how the architectures were evolving and why. At the beginning, I will tell a little bit about tokenization because you know we need to feed the words or the information about words to the neural network somehow. And initially, we were working with phonemes, with words, or with characters. But if we want to work with words, and we want to have all words at the output from your network, so if we have million of words, we need a million of output basically neurons. But this is not practical, and for example, for Czech language, we have several millions of words that we would need to model. So to work with words directly is not practical. Therefore, we were looking for smaller units, for some subword units. And the most common subword units are byte pairs and word pieces. With byte pairs, the algorithm is simple. We just start with characters, and we count the character statistics, and then the character pairs that are the most common are merged together, and we continue in this way until we reach the number of units that is reasonable for us and that we will use for the neural network directly. Word pieces, it's a similar algorithm. Instead of working with the statistics directly, it estimates or trains language models, and if we want to add a new unit, basically we evaluate what is the increment of the likelihood of the model. And again, we iterate until we get the number of units that we like, or if the increment in likelihood stops growing, it is other signal that can be used to stop the process. Okay, now I will skip to the neural network architectures. As I said earlier, we started with simple neural networks like three-layer feed-forward network. And it was doing something. We use it, for example, for phoneme recognition, but the architecture was not powerful enough. So here I will start with factorized time delay neural network that was very popular in speech processing. And you can see in speech processing the difficulty in training was always the amount of training data that we had to train such network. If we have enough data, it would be okay to take a block of features and train the neural network and increase the acoustic context. Usually, the longer acoustic context, the better. But in practice, if we were increasing the acoustic context, the accuracy stopped growing at some point. So here you can see a pyramidal structure. Here is one frame, and each of the higher layers was looking on a higher context. There is some sparsity, not all there are not all the connections, and you can see it is looking more in the past and only fewer number of frames to the future. So this neural network gave us already very good results. We were using it for speech recognition, for speaker identification, and other tasks for quite some longer time. And as I said, there was a difficulty in the number of parameters because of the training data. Here there was other trick. It is factorized, so it means that the matrices among each two layers were, it was not only one matrix of weights, it was factorized to multiplication of two matrices with lower rank. So there was fewer number of parameters. Okay, so there was always question how to work with the past and if we can use recurrency in the neural network and if the recurrency can process longer context. Theoretically, with recurrent neural network, we can model infinite past, but in practice, basically the gradients are decreasing very fast, and we see only a few frames to pass. So there was very famous work from Tony Robinson, for example, where he successfully used it for phoneme recognition, but this is the difficulty. Therefore, people start thinking how to improve these recurrent networks, and the long short-term memories came. What you can see in this network, that there are new operations, there is multiplication in the architecture. This is called gate. These gates help to keep some information for a longer time or to forget some information very quickly. And here in this architecture, there is contextual state, and there is input gate that should control the information that is coming. There is output gate that controls what goes to output, and forget gate that controls what will be remembered. So in practice, it can learn this kind of network can learn short context, but even longer context in past. So in practice, the gradient decrement is not so fast, it is more linear. Okay, so this was about LSTM. Practical or experience, the network used to be run from past to future, but for a different evaluation in competition, you were forced to get the best results. So simple engineering trick is to basically turn the audio and send it to similar network, and if you can do it, you can do it once from the past to future, once from future to past, and such approach is called bidirectional LSTM. Okay, but as I said, the long short-term memory was already better was working better with the acoustic context, but it was still not optimal. The ideal situation is if we can select or train what is important for us, what is important for recognition of the current word, if it is something from past, if we have recording, we can look even to the future. And people start thinking about attentions. This concept is important because it is the main concept of transformers, but I will show you on the implementation from listen, attend, and spell model at first. So here we have speech features. And we would like to basically get the important information from these features for some state. So here's the state can be, for example, phoneme, or basically some sound. And this information we are looking for is characterized by a vector, by a state vector. Okay, and how we can get the important information? So we need a function that shows maximum when the wanted information and the information in our data match. And this function here, we can use simple dot product. But to ensure that this dot product is able to get the maximum, we need to transform both the features from audio and our state vectors by a function here, by neural networks, to ensure that if we have important information, we get maximum by this dot product. And so after this product, we get basically a function that says this is important, this is not important, this is, for example, important. But then we would like to weight the importance. Let's say we need to distribute some mass, some probability among the important parts. So we use softmax. This softmax basically normalize the attention weights to sum to 1, to be sure that we really distribute our attention, basically the mass to different part of audio. And so here we got attention weights, and what is the next state or next step in the processing? We take our input vectors, feature vectors, and sum the feature vectors with the attention weights, and we get one output vector. So this one output vector should contain information about the state or the phoneme that we are looking for, and the information is extracted from the whole acoustic context. So this is quite important. Are there questions to this approach, or why are there the blocks? Because with transformers, it will be a little bit complicated or more complex. If there are questions, I will repeat it. Okay.
Is the attention between each segment of features?
Yeah, imagine that this is sequence of feature vectors, and imagine this can be a recording. Here is the beginning of a recording. end of recording, and you have state vectors, and you are extracting the important information for these states from the whole recording from all features. So there is a weight for each of the feature vector, how the feature vector is important. Okay, now how this approach is used in listen, attend, and spell system. So at the beginning there is encoder. You can imagine it as basically acoustic model. It is BLSTLM with pyramidal structure. So the structure is not important for us now, but it's some kind of subsampling. We are compressing the information, and then you can see that there is this state estimation. For the state estimation, there is a recurrent neural network that estimates the state based on the previous state. The feature vector, basically this that was that you obtained from the attention mechanism, and based on the previous labels that were already recognized. So it is here. You can see this this came from the encoder. Here the state. Yeah. And what I didn't mention, basically, or how to look at this picture. Here you can see the input. This is basically loop that here we have output labels. So the output labels goes again to the input. So this is this, and here we have this edge. This is this are the feature vectors that goes or feature vectors that I showed a while before that came from the encoder, and C is the one vector that got all the information from the input vector with the contextual information. Now I will move to the transformers on next slide, but I wanted to add quick remark. I think now the most or widely used architectures are transformers, but the transformers are not practical for online or real-time processing. So in parallel, there was or there is architecture RNN transducers that you can find in your phones. The offline recognizers that runs on phones are using this architecture, and there is encoder. There is prediction network. This is more. The prediction network is something like language model. Then there is joint network that decompose information from both acoustic part and language model part, and then there is softmax. The outputs are characters or phonemes or some labels, and then there is, this works autoregressively, and there is loop to the input of the predictor. Okay, what's that? Okay, so now I will move to the actual and more funny parts. Many of you will use transformer during this workshop, and you will extend models based on transformers. So it is important to understand what transformer is and how it works. I will start with the terminology in transformers at first, because if you start reading about transformers, you quickly found that there are some queries, queues, values, and what does it mean in this attention mechanism. So I have here the picture again. Just to remember, we have some feature vectors that we extracted from audio in our file. The dot products tries to find the important information. The information is selected based on the state vector SE, and there are two neural networks that transform the state vector and the features to ensure that the dot product gives the maximum where is the important information. Softmax normalize it over, let's say, time to sum the maximum information. The weight should sum to 1, and then there is a final part where we sum the information for the selected frames with the weights. So what are the queries? The queries in transformers are basically these state vectors. The keys are is the information that is coming from our features from the audio, and this goes to the selection, and values goes to this weighted sum. Why they have keys and values in transformers? They can use different values because they are able to merge several streams. One more remark, this basically, or even the listen, attend, and spell, or the transformers, they usually say it is encoder-decoder architecture. So we have input sequence. We convert this input sequence to some intermediate representation using encoder, and then we have decoder that generates output sequence. Now, how the decoder works, this is quite important. It works in autoregressive way, because we have encoder, we generated a sequence of vectors, and now if we have decoder, it's usually other neural network or part of the neural network that estimates the probability distribution of symbols for each basically time step, for each output symbol. So we run the decoder and generate the posterior, the probability distribution of output symbols. If we recognize, for example, characters, it will be the first character in sequence, and then we can work with the probability distribution. We can select the most probable token character, or we can do something, we can do some sampling, and this goes back to the decoder. In the decoder, we are working only with symbols that were already produced in previous steps. Everything that goes to future is masked, or there are zeros. So can you understand how this decoding mechanism work, or maybe other questions?
What does autoregressive mean?
Sorry?
What does autoregressive mean?
It means that it generates one symbol each time, each step. That it starts with, for example, one token, and then it needs to go through the process for the next token.
And what's that sampling part?
Here you have probability distribution. So it means that you will get probability for each of the possible output tokens. And now it's on you, what will you do with this probability distribution. You can, for example, take the token or the character that gives for the maximum with the maximum probability. But you can do other tricks. If you, for example, want to more random output sequences in the decoding, different answers, you can do this differently. Okay, now I showed you the picture that is in the original article from Google, and this shows already the whole transformer. So there is encoder on this side, and there is decoder on this side. So we have input, these inputs, for example, if there are words, we need to encode it, and we encode it with some vectors, so we can do it using a dictionary that we have, for example, for each word dictionary, how it was trained. It's different way. For example, initially it can be one hot encoding that we have vector with zeros and one for token for the word, and yeah, but we usually with neural network we convert it to some more dense form. I will speak about positional encodings later. It is not important now. And now here you can see that there is a block multi-head attention. Let's imagine that it is dot product attention, and it is exactly the same mechanism that I showed you a while before. you can see that there are 3 inputs to this block, queries, keys, and values. And this part compress or extracts the information from the context and produce these contextual enhanced vectors. You can see that there are some new, things that are commonly in neural networks, like skip connection and normalization. And after the attention, there is feed-forward neural network to do some transformation. So this encoder is doing the attention in respect to the input, the input features or the input embeddings. So this is really what we saw a while before. This is some kind of transformation that gives the model higher power. But in transformer, we have some input sequence, and for example, in translation, we can have output sequence. So what we can do exactly the same, but with respect to the output sequence. So again, we can have some output, for example, words, so we convert it to embeddings, and we can have attention to the output sequence from our transformer. What is different here, that usually we don't have here the future. That really we process here everything till the actual label or token that was generated in the previous iteration. Okay, so now, till now, we have basically two streams. One extracts information from the input, one from the output. But now there is other part. We would like to merge the information from the input with the information from the output. This is done through other attention. Here it is called cross-attention because it mixes information from the input and from the output. And you can see that from the output there are going the queries, basically the state vectors that are saying what we are looking or what we would like to look from the or what we would like to extract from the input stream. Then the keys and values are extracted from the input stream. So from the output we are saying what we are looking for, and the information is brought from the input. Then there are again some layers like normalization, feed-forward network for translation. And the question, there was a question, what is autoregressive? I again showed you this loop because for each output symbol we get some probability of distribution of possible token. So we need to do something with the probability distribution, for example, to select the best one and send it back to the transformer through the output branch. So what we are doing, we have a string of output tokens, and each time we extend this sequence by 1, and the rest is basically 0, because we mask what is in future. We don't know what is in future. We try to recognize it or transcribe it. Maybe here, because, okay.
I have a question. I can understand what is the purpose of attention layer, but I don't understand what is the purpose of feed-forward in this context.
So you are getting here. You are getting some contextual vectors, basically input vectors that are where you are that are enhanced with information from the context. This is the attention, but now you would like to add more information, basically already to train the network for some task. This adds the modeling power to the architecture.
Okay.
It's, yeah.
Another way to think about it is that in a normal neural network, when you go from stage to stage, you carry out some nonlinear transformations of the input, right? If you think about it, the multi-head attention part, it is only doing linear things to the input. It's taking the inputs and combining them in some linear fashion to produce the yellow box, which is called add and not. So there is no nonlinear. I mean, there is nonlinearity in how the weights are computed, but that's only computing the weights with a linear combination. And then that yellow part is still linear. So this is the real original part of the neural network, the feed-forward, which is going to do the nonlinear transformation. So together they form one layer of the network. But before you apply the standard neural net block, which is the feed-forward block, you do some internal reorganization of the inputs by saying you can linearly combine some of the inputs to create a new input before you do the transformation. And that linear combination is that multi-head attention part.
And another question. I think I see what is the input for feed-forward, but what is the shape of the output?
You mean here or?
Yeah, like the output after the feed-forward. So in outputs of multi-head attentions are then fed into feed-forward, right? And what is the output of feed-forward? Does it have the same shape or like somehow reduced shape?
In transformer, basically they try to keep the same shape, and there is the same repeated several times. And actually, the answer from Sanjeev was excellent. Maybe even as I showed the exact implementation of in this listen, attend, and spell architecture, there the neural networks are here, and their networks really transform the data to get the maximum for the selection. So we need the modeling power, this nonlinear transformation, and here in this architecture is in this part. We had a break just before this. Okay. Now, actually, till now, I was speaking about sum dot product attention. This is almost the same as I showed before. Here it is written in using matrix operations. I will explain this on the second slide. But imagine that till now you had mass, for example, 1 or 100%, and you had to distribute it, the attention among your input feature vectors. But imagine that you would like to for example, do the translation from one sentence to another sentence. There probably may be different possibilities. The same output sequence can be pronounced differently. It can have different structure. In the language, you can say the same in many different ways. And this is probably what this multi-head attention can do. You can imagine that you would like to have different inputs, different input sequence, for example, sentences, and map it, for example, to one output. And through this multi-head attention, you are getting higher modeling power to such architecture. Of course, you need to do some processing for it. So here there is linear transform in front of this multi-head attention, one for each head and each value key query. This is closer to this, that implementation in latent, listen, attend, and spell architecture. After you concatenate three attention or these contextual vectors from attention, and again there is linear layer or that combines the information from the heads. So it's a way how to really increase the modeling power. On these slides, I wanted to show that really this, what is on this picture is the same that I showed you a while before. So here you have the multiplication of Q and K. If you do the matrix multiplication, you can have this row and this column, and it's basically nothing else than the dot product. So you are doing it for all to get this QK. I am not showing here the softmax. This is normalization over the row. So if you look at the attention on this matrix, you should see in each row some graph that shows what in the input is important and on what position. But the softmax is not here. It's done in the transformer, and then again there is a multiplication of this QK times V. This is the weighted sum that I showed a while before. There is one scaling. Basically, they said that if they did it without, it was not numerically stable because with large matrices, it was not stable, so they used this normalization, this scaling. And now there is this part. This is not obvious if you look at the picture at the first time, but if you are working with these input embeddings, you have these queries, keys and values, but the architecture doesn't model relations among the frames. It can be done in different ways. some architectures are using convolution networks in this embedding part and can add a relation among phrase natively. So the position embedding is not important much in this case, but if you are processing, for example, text, you need to model somehow the position of your words. And in transformers, they are adding signal to these embeddings. The signal is added basically by, it's added by operation, and the signal is sinus or cosinus with some frequency. There is a different function for each dimension. So the first dimension is sin, the second dimension is cosine, then there is again sine. They use these two because they are orthogonal. So they are better for modeling. And if you can see, pos is basically the index of input token. I is the embedding or input token or input vector. I is the dimension index inside the embedding vector, and this is basically the embedding size. So this is a way how to preserve the position information for your tokens. This position embeddings are basically it works for your recordings. There are different ways how to do it. One is using some convolution networks. Other is to use, for example, relative positional embeddings. But it's important that there is some mechanisms like this. Okay, I think this is the basic information for the architecture. If you have some more question about it, please ask, because then I will go.
Yeah, I have a question. Do I understand it correctly that this input embedding is represented as a list of numbers, and when we add positional encoding to each number in that, we compute like some extra number and add to it?
Yeah, exactly.
Sine or cosine, and the model is capable of seeing these, like understanding that there is some like sine cosine thing, and that's how it understands some kind of positional ordering.
Yes, exactly.
Okay.
Okay.
Some models using convolution to decode the position. Like, why there are different methods? Is convolution better in some cases?
It depends, probably application by application, but if you have this convolution, the convolution sees the context itself, so it can give some positional information. The convolution networks, it is probably for shorter context, but it works. Okay. Now we were speaking about transformers. You see that the architecture is quite complex, and the architecture can be adjusted for particular application, particular tasks. So some parts of the transformer are not necessary and for some task, and our models can be simplified. So we said that there is encoder, there is decoder, but are these parts necessary for all tasks? No. So there are architectures that are using only the decoder part. So these are basically tasks where we need to generate something, where we need to generate, for example, code, answer questions, follow some instructions, and these models, the most famous kind of these models is GPT or the follow-up models, Llama, Mistral, Palm. So basically, the models that if you type GPT, so you are interact with this kind of models. Then there are encoders-only architectures. These are good for classification tasks because you can extract, for example, one vector and add more some heads or like neural network parts that are task specifics, for example, for sentiment recognition or tasks like this. So the most famous model is probably the BERT, Roberta, Distelbert, and so on. And then there are architectures that are using the whole encoder-decoder architecture, and these are good for translation tasks, text summarization, paraphrasing, question answering, text-to-text mapping. And here some examples, for example, T5 from Microsoft, BART, from our domain, Whisper. And
where would you put models like RLM or R2A? Would you call them encoder-only models, or would you call them something else?
This is good question. Maybe I have wave to wake on the next slide, and actually now I have application for all three examples for all three classes, and I have wave to wake as one of the example that I had in the presentation in past, and we can look at it and then decide what it is really is. But it's a great question. So, okay, I will say what is wave to wake, and then we will show the picture. Actually, in speech processing, models like wave to wake, Hubert, Llama got huge popularity. Here is my explanation of why these models works. We want to train models for all possible languages, and to collect the data is extremely costly because it's different if we collect data for one language, for example, English, or whether we collect data for all possible languages on the planet. But if we learn a model for a new language, we probably can utilize the information from other languages. So my explanation is that we have some anatomy, we have vocal tract, and so on. We are using the shape of the vocal tract and so on, for example, in speaker identification. But I think that the possible movements of the human auditory system is limited, and it can be modeled, and with some data, we can basically learn what are the states of the human basically the vocal tract and so on. And we can encode the states with some vectors, some again hidden representation. So here is basically the wave-to-vec architecture, where we have here we have input speech. The speech is encoded using some convolution networks to some embedding representation, and then we have two branches. In one branch, we do vector quantization and quantize the information coming from the convolution networks to some limited number of vectors, and in the second branch we send the information through transformer, and at the input of at the output of transformer we try to maximize or get the same, maximize the similarity. There is this contractive loss. So maybe now is it transformer, encoder, decoder? It's not there is not everything from the architecture that I presented before. There is different there are these convolution networks. So I would say that there is encoder. So now the question: do you see decoder? Or? Yeah, it's probably encoder. So yes, and so there is diversity lost. What is important? This vector quantization is not done in advance, but it is a part of the overall structure, and it is trained together with the whole model. So you are really doing gradient descent, and you learn even this quantization. There are some tricks how to do it. I won't go into the details here. And there is a diversity loss that basically ensures that our code book is there is enough vectors in our code books that it won't collapse to just one vector, but we will get really the number of vectors that we expect. And if we train this model, the model, how it is trained, this is another important question. We have this input, and we are able to mask some part of the input, and so it's mask input, and we train the transformer to get the whole the whole input, and as output from this architecture, we are getting basically these quantized embedding vectors, but obtained from this transformer. So these embedding vectors are like features for our other tasks. So I would say this architecture is quite complex and quite difficult to understand, but this approach got huge popularity because it is seen in many tasks everywhere. And there were other two approaches that came later. One is Hubert. You saw the vector quantization, the implicit vector quantization inside the neural network architecture is quite complex. So the Hubert just took MFCCs, coefficients from speech, and used k-means clustering, get the clusters, and here, instead of these clusters, they just used these k-mean clusters and trained the transformer. So it is easier architecture, and it works almost the same. And other popular system. This is my explanation. So I'm sure that there'll be some research in this direction, but this was my explanation how to basically to imagine why it works. So Hinek, do you know about research explaining, for example, this wave-to-wave representation and mapping it to the human vocal tract? And yeah. Okay, yeah, it was my explanation. So in this paper, they mentioned that the primary use case is speech recognition or speech transcription. But for example, in this wave LM, there are many downstream tasks, and they even are using other optimizing criteria. They are using mask speech prediction and denoising that they claim that is even better for this downstream task, and that it's better to preserve, for example, speaker information.
Maybe we can say that we are encoding all the information existing in the speech, not just the vocal tract, because the linguistic, the speech-related features.
It's probably that there is more information that only what is inside the speech, this vocal tract.
I think it's also related to the CNN that comes before the transformer layers. Because the CNN has like 5 CNN layers with different stripes. And so you have low resolution at first on the early layers, and then it's higher. So the information that's encoded is fine-grained depending on how many layers you travel through. And this is why in the transformer layers, which come after the CNN, you have
It's true that, for example, for some task, not the final representation is used, but very often even the information from lower layers is used, for example, in speaker identification or other, or even the information from various tasks is combined. So at different level, there will be different information, and I think that as we go further to the final representation, more and more information for some downstream task is lost. I think we didn't answer it fully, but we can continue in discussion later. Okay.
I didn't quite catch the question. What was exactly the question? Maybe I don't hear very well. What was the question?
It's not.
The processing inside.
I showed the example with this human vocal tract and with this picture. And if there is a research that maps this representation to the vocal tract, or whether it is just my explanation.
Maybe I will try to mention it tomorrow during my talk. Recently, people are looking at the time constants at different levels of the processing, showing that as you would expect, as you go higher and higher in processing, the system is looking for longer and longer segments, which is very similar with human perception also, what has been observed in human brain. So that may be one. The other one, which is interesting, which actually Hubert should talk about, that interesting thing is that first layers of this convoluted network are doing basically spectral analysis, which is kind of surprising because there is nothing hardwired built which you do spectral analysis just like Fourier transform. This is what the network is learning. So there's a few things, and maybe we can talk a little bit more about it. I'm sorry, I didn't quite understand the question because you are far from me. And
there are two papers from Kita Pasat, I don't know if you remember. She's doing all this work about this kind of supervised encoders and all information they retain, so from phonetics to semantics, and there are some.
In fact, I intentionally asked this question just to say we are not just modeling the vocal tract, as we all the members discussed. We are modeling many things based on the layer, which layer we are getting the representation, not just the vocal tract effort or vocal tract information. Because of that, I asked this question, and now it's more clear for me. And as our topic mentioned, for example, in the conformers, we are getting semantic information based on the longer segment. So just to, I asked this to not simplify the content of the representation given by the SSLs.
if I may, I was thinking while you were talking, there are two possible connections to the vocal tract aspect I was showing. One is the way the speech being produced, information about the movement is spread in different parts of the spectrum. Subsequently, this model is looking at different frequency channels because it tries to then collect this information from the wide spectrum
Okay, so I'm glad that I did opener for Hinek's talk. So you can discuss these topics for 2 hours tomorrow. Yeah, and but I will show.
Maybe just to add one thing, when you are training these models, they definitely try to capture more than just any thinkable articulator, which I'm sure that if you try to train to predict those things, you will predict those things. Hard to say when you predict from more than pure acoustic information or even from knowing what was being pronounced and then trying to revert the things, what the articulator would be responsible for that. These models are actually learn internal language models because they are trained in such a way that they is much more than just some local acoustics information was articulated. It learns which word is in the context of which word, so modeling much longer temporal dependencies or linguistic dependencies, so it's definitely more than that. But I guess that Petr wanted to just say that you can learn something like that.
Yes, actually I wanted to add some justification, but I should have mentioned that it is not the only one justification, that the use cases are wider and the justifications. When we were training speaker ID systems, we were always using many different features that were not supposed to be, were not developed for the task, and we were always able to get some information out of it, so it's the same case.
And maybe I would say just these pre-training methods are just, the models are trained to make sense of the structure in the input data, whatever that means. I mean, there is a structure in speech, there is a structure in language, and when you train these models, they eventually are forced to make sense of the structure in the
Yeah, but you need to ask, what is it that you are asking to do the model? Tries to predict something which is not too far from what now, making it in several hundred milliseconds. So it relies on the similarity of the information within the certain time constant. Subsequently, that's what you see. It's not very smart. It just looks for some very basic property of speech, which is like if the speech is running, things which are close in time are similar, which are far in time are different. That's what the model is being trained on, contrastingly, or basically tries to predict what you mask, and what you mask is something which you probably can also predict. I mean, that's the way I see it. Lukáš may not.
Okay, but sure, but I'm just saying that you eventually, for example, mask the whole board, so you cannot even say seeing from the acoustic context, I could predict that the articulator track to move this way. No, you actually are forcing the model to predict the whole word in the context of some other word, but it needs to make sense of
Well,
it.
word in general is about 700 milliseconds, right? This is still reasonable. It's similar.
Okay, I'm sure that you have a lot of topics for tomorrow presentation. Yeah. I will move to other major use case of transformers, and this is GPT system. So here you can see how it looks like. So it's the decoder architecture. There's text embedding, again self-attention, and what you see then the layer norm, feed-forward network layer norm, and this can be trained to predict the next token, the next word, but after that you can add many classification tasks. So such architecture is trained to predict next word initially, but the other task that it can be used is like classification, entailment, similarity of two sequences, multi-choice answers, and so on. Just to see how it looks like from the math point of view, you have the input tokens. This part is the embedding. So you take the words, you embed the words to embedding vectors, so you add the positional embeddings, and then you have the transformer block, and after that there is the softmax that generates the probability distribution of tokens exactly as I explained it before. Here the objective is this, we maximize the log probability of our data, and for the supervised task we can add linear layer softmax, and the objective can be, for example, this. And even for the supervised fine-tuning, they claim that if we combine both objectives, the training is faster. So the basic model is very simple. What makes GPT very usable, I think, is the instruction training and basically the work with data. If you are interested, I think the most informative article is article about Instruct GPT from OpenAI, and there you can see how they collect the data and improve the model with crowd. So there was first step where people were asked, for example, explain moon landing to 6 years old kid. Some people wrote the text, and the GPT here in this article is GPT-3, was fine-tuned for such task. So even this model was able to answer this kind of questions, but this model was also hallucinating, and it was generating answers that people don't like. So the other step was that there was other group of people, and they got several answers, and they were asked to rank the answers. For example, A, B, C, D, which one is the best, which one is the worst. And if there is such ranking, it's possible to train a reward model, basically model that is doing the ranking itself. And if there is such model, it is possible to use it in our training and retrain or fine-tune the model with this reward model. So this was done in this last step using some kind of reinforcement learning techniques. This is one huge application of transformers, and I am sure some of you will work with this kind of architecture. So this is decoder-only architecture. Then from the other side, encoder-only architecture is, for example, BERT. Here it was trained as a masked language model pre-training. So what does it mean? We have transformer, we have text at the input, and we want to predict the text on the output, and for training we just mask, they said 15% of tokens, and we try to estimate such tokens. so it's not fully autoregressive in this way, but it's masked language model because there are gaps in the text itself. And then there was fine-tuning on many NLP data sets. So for example, there were tasks that actually even for pre-training there was one more task. This was next sentence prediction. So there was sentence A, and the model was asked to predict sentence B. So mask language modeling and then next sentence prediction were the two tasks for pre-training, and there were many other tasks for fine-tuning. I have some of the tasks just from the first benchmark data sets. So you can see that there is again entailment, two-question similarity, sentiment, is the sentence grammatically correct, how similar are the sentences. Such tasks were fine-tuned, and then you were able to get one vector for the whole sequence, or for the recording, and with some embedding, and you took other neural network or some other layers that were trained for tasks that you wanted to solve. For example, if you were doing sentiment analysis, if is the text with positive sentiment, people like the product, or negative sentiments, won't buy anymore. So you were able to take the embedding from the BERT and train other classifiers for such tasks. And the last example that I have here from transformers is Whisper. So everyone knows Whisper. It's so popular. It's speech recognizer. You can see here encoder blocks, decoder blocks. There is some convolutional net for the input embeddings. And what is special, because everyone uses it now, it's simple transformer architecture. There is not much fine-tuning, but this is key. It was trained on 680,000 hours of data, and it was trained on many languages. And also, what is interesting, it was not trained only for speech transcription, but there are other tasks. There is voice activity detection, language identification, translation, I think translation from different languages to English. And what are disadvantages of such architecture? It was trained on segments that are 40 seconds long. So if the sequences or the recordings are longer, there needs to be some auxiliary processing. And also this transformer architecture has disadvantages with real-time or online processing. So for online processing, the people use different tricks. They are sending the audio to the encoder again and again, so the processing is more costly than different architectures. Okay, so for me, for example, this article or this image is interesting. These two images are from the Whisper article. And here you can see how the information is encoded. So you can see that there can be tag start of transcript, there can be language tag if it is speech, there can be non-speech label, and if there is speech, it can transcribe, and if we transcribe the audio, it can produce and time labels because it was trained on videos with subtitles, and there was the time information. If it's translate, so it means that the audio is, for example, originally in English, and we have or other language, and we have text in different language, so there are no time steps, there is just the text, and then basically some final symbol. So this basic architecture and pictures shows how the transformer can be powerful, and I'm sure that, for example, Lukáš will have more in his presentation, and you will be working on architectures like this here on these workshops. So I think this is all from me at the moment. Thank you for attention. And if you have any questions, you can ask now, or I will be around, so you can come anytime to me, and we can discuss the things that are interested for you.